We are both students from the Architecture School of Paris-Est, at the master chair called Matière à penser, which somehow means thinking by the material. The master's thesis is built in two parts: writing an article analyzing a structural system and building a Scale 1 prototype.
Our article is studying circular meshes, which are a very complex subject that we try to make it easier to understand. Meshes are used for parametric conception of surfaces as a tool to optimize the shape of the surfaces thanks to geometrical rules. The aim is to design well-optimized surfaces that bring to a material saving. The circular meshes are a tool to discretize a surface into squares. Each circle of the mesh has a square inscribed into it. Thanks to it, the surface is decomposed in planar squarehead faces. This is used to design grid shells with planar curvature lines and planar nodes. But we were more interested into describing the use of circular meshes to design shells made of circular section modules. Those kinds of structures are made on a quest to experiment new use of various materials. This article is describing really easy and frugal principles to build fast and lightweight with a high efficiency.
The article is describing two circular meshes. The first one, the circle packing mesh, is a triangular mesh whose each triangle is included in a circle. All circles are tangents and create a packing. This mesh is easy to manipulate and to parameterize, but it doesn't offer a large panel of double curved surfaces. The Isoradial mesh is composed of circles with a unique radius. Each of these circles is circumscribed by a planar quadrilateral face, which forms a grid once associated. The generation of this circular mesh with planar lines in both directions is made from two curves that cross at 90 degrees and which are guides called directrix and generatrix. The grid of the final mesh results from their translation in two directions. This technique helps to design free-form surfaces unlike the circle packing mesh.
We will see several ways of using circular meshes with three different case studies. The joints between circular modules are significant because there are no edges, so they had to develop assembly strategies. Artist Vincent Ganivet's stylo was made from the Isoradial mesh, where the circles are all inscribed in quadrilaterals. The modules are made of reused tires of identical size. The connection between four tires is created with concrete, which is able to mold the round shape. The Pneuhaus collective's bubble dome is a half sphere. The assembly is made of a flexible structure that blocks the spheres together by pressure. Here, the geometrical rules of the circle packing mesh has been used to design the dome. As a second example, the Shadow Pavilion was built from the circle packing mesh, where the circles have evolving radii. This variation allows creating more complex shapes than with invariant circles. The modules of the Shadow Pavilion are made of curved aluminum sheets that form cones of different sizes. This flexible material is stiffened by the curvature while ensuring its lightness.
We chose the Shadow Pavilion as a reference to design our Scale 1 prototype. The way of turning a sheet of a flexible material into a rigid module was an interesting point to deal with. We have chosen to work with the circle packing mesh rather than the Isoradial one due to its easier handling with Grasshopper software. A triangular mesh was applied on a double curved surface created. Then, a circular packing is applied on the triangular mesh. All the circles are tangents. The parametric model allows a real-time modification of the surface in order to preserve the tangency between the circles. This tangency is a crucial issue for the prototype fabrication. It guarantees its constructability and a contact between all the circles, which provides the load transfer through the structure. This process creates irregular and variable cone shapes according to the original surface curvature. The modules are tangents along their lengths. They form membranes that allow the disc from the circular packing to be stabilized. This inertia varies under the loads. The stiffeners and the conic modules have been made of cardboard. Once rolled, it becomes rigid. Then the conic membranes and the disc are joined thanks to tenon mortise system, which offer an interlocking and perpendicular contact between both elements.
The construction process has been studied to keep the lightness and to provide a fast fabrication easily repeatable. It was possible thanks to the use of a numerical tool as the ladder cut. We choose to use stepless to close the cones around the disc, but also to join all the modules together. The aim of this research was to create an easy and fast-made structural system that could be developed for images construction or ephemeral installation. These circular element shells emphasize the opportunity to build lightweight structures with reused materials. These shells of circular elements demonstrate a search for lightness and ease of implementation.